Hi, I'm John Duggan, and this is the TheoryStation. This program is the Principles of Math program. The series is Basic Ideas, and this is installment number 8. So in the last couple installments, I talked about functions and maximizing a function. Here I want to sort of elaborate. We've already seen that ideas in math can start simple, and then they start you build on them and make them more complex. So we're going to build on the idea of a function here, and we'll talk about multivariate functions. Okay, so far we've talked about a function of just one variable, x. We plug in x, and this gives us some number y. In particular here, x is just one real number. And we know how to graph that sort of thing. If this is our f, you can imagine you plug in an x, and then that gives us a y. You can do that for any x. All right, so a function is just, I mentioned before, it's like a machine. You plug something into it and it gives you something back. Well, you could plug in not just one number, but how about a pair of numbers? Okay, well, that's fine. You can plug in a pair of numbers. And then it gives you something back. Well, these can be very general, but why don't we just go with a specific example where the function just adds x and y. You plug in x and y, and it gives you the sum. Okay, so this is the summation function. It's not a very exciting function, but it's definitely a different idea than what we saw before, or at least a more complex idea. Now, how would we think about this function graphically? This is something I like to do. Well, if you want to be literal about it, before what we did was we had the input of the function on the horizontal axis, and we gave the output on the vertical axis. Well, we could do the same thing here. We can, but now the input is not a number, it's two numbers, and we've seen that that is like, we can represent that with the Cartesian plane. Okay. So I'm going to take that Cartesian plane and lie it down flat. And then the values, the output of the function is going to be on this vertical axis here. And so you can imagine if I take some combination, some x and y, excuse me, the function is going to add those up. And that's going to give us, we'll indicate that sum by this vertical distance here. So if this is x and this is y, that vertical distance will be x plus y. Now, this is going to be hard to draw because we have to do that for every point on the Cartesian plane. So let me do this in blue. The way I'm going to do this first is I'm going to do it for every point on this x-axis. Okay. Well, on the x-axis, y is equal to 0, so the function is just going to give us x. And so the graph of the function will look like this above the x-axis. Okay. I can do the same thing over the y-axis. So there, x is equal to 0, and so the function is just going to give us y back. Okay. And then suppose at some value of y like this that's non-zero, let's again think about, let's fix that value of y, increase x. We're just going to be adding x to that y. Yeah, it should be parallel. We're going to be adding x to that y, like so. We can do that for any value of y. Or if we fix an x, we can add y to that. And looks like I'm a little bit off here. And so if we were to try to visualize what the graph of this function looks like, it looks like this ramp that is flat but tilted up and extending forever. Here I've just drawn it extending in one direction, but it would also extend back. And it's going to be hard to draw the whole thing. Okay, that's kind of laborious. You can do it, and I actually think there's some value in being able to do that. So that's what the graph of a multivariate function would look like. A different way of picturing multivariate functions, though, would be to say, well, let's pick a value of like 7 and ask, what would if we look on the Cartesian plane at these xy pairs, what are the xy pairs such that x and y add up to 7? Okay, so notice I'm using this curly brace notation again. It's the xy pairs on the Cartesian plane such that they have this property that the function evaluates to 7. Obviously, that's just the same thing as saying x plus y equals 7 because that's how the function is defined. Okay, so let me just put that in. Well, we can picture that as well. That set is going to belong, it's going to be in the Cartesian plane, right? So now I'm just going to draw my x and y axes. And it's going to be xy pairs that are in this relationship. Of course, x plus y equals 7. That's the same thing as saying y equals minus x plus 7. But that's the formula for a line in the plane. So we can graph that. And if this is the value 7, the graph of that line is going to look something like this. Okay? So the set of values where the function takes a value of 7 is just a line. What about the set of values where it takes, what about the set of pairs where it takes a value of 8? It's going to be a line again. What about the set of values where it takes the value 6? The set of pairs where it takes the value 6, well, that's going to be another line. And, well, these are all going to have slope -1. So they're going to be parallel straight lines. I could draw more lines in for different values of the function. Now, if we go back to this three-dimensional figure that I just did, if you think about it, the three-dimensional picture, it's a picture of this ramp kind of extending forever. The two-dimensional picture is like a topographical map of that ramp. Okay. Remember, a topographical map is, well, it's a bunch of curves and or in this case lines, and on each curve those points are all the same altitude. Okay, and that's what we have here. The set of points where the function takes a value of 7, well, that would be the set of coordinates where the altitude of that ramp is 7. So this topographical map idea, it's actually much easier to draw or represent functions in that way. And so that's something that we'll do quite a bit. Okay, so there's other functions, of course. Multivariate functions, they abound. You can have any number of inputs. So here n's a natural number. Oops. And here's a function of n variables, okay? And that can have any kind of form. If we want to stick with something that's kind of additive or linear, you could imagine just defining this as the summation function. Okay, that's not the most exciting kind of function, but just a possibility. Let's go back to a function of 2 variables and think about a function that does not have that kind of linear additive structure. Let's multiply these things instead. Excuse me. So this function is, well, this is going to be so this function is a little bit more interesting to draw. If I do the 3-dimensional version of it, oh, excuse me. So if I fix y equal to 0, then, and I let x vary, then this thing is just x times 0. So it's 0. The function takes a constant value of 0 on this axis. Similarly, it takes a constant value of 0 along the y-axis. But if I make y positive, the function is going to, and I increase x. So let me just so now I'm going to increase x. Now the function is going to get bigger. Let me use blue for this. The function is going to get bigger like so. Because I'm increasing the x, and the x is multiplying y, which is positive. All right, let's pick a bigger value of y and think about increasing x again. What's going to happen to the value of the function? Well, it's going to get bigger. But now it's going to get bigger faster because I'm multiplying x times something bigger. So I'm going to, again, draw this line, but it's going to be steeper than the first one. And I can keep doing this. I'll only do it one more time. Now I'm multiplying x by something. Let's make it even steeper. Very big. Okay. At the same time, I can do that for the symmetric situation where I fix x at something positive. And now y is going to get bigger at some constant rate. I make x a little bit bigger. Increase y, it's going to get bigger faster. And so on. Okay, so it's maybe a little hard to see what's going on here, but this function is going to not be a ramp that extends forever. It's going to be, wow, it is hard to describe. It's kind of a giant scooping shaped thing that starts, well, it scoops upward and just starts getting super, super steep. I don't know how to explain it, but if I were to draw say, rings around this shape, you would have this kind of shape. That's a mess to look at. Okay, so let's go back to our topographical map because, well, now you're seeing why. It's simpler to look at. So let's look at the set of xy pairs where the value of the function is equal to some number. Let's pick 7 for the heck of it. But, all right, so let's divide by x. So here I'm going to be focusing on the pairs where x is non-zero. So we have this relationship now, but it's not a linear one. So for the pairs where the function takes a value of 7, if we pick an x, the value of the function that makes the function equal, the value of y that makes the function equal 7 is 7 over x. Okay, this relationship we can graph, and it looks something like this. Okay. We could take any value of the function. In fact, we can make this more general and just take some value, let's say v. And then, we can still solve for y in terms of x to get this kind of functional relationship. This describes the xy pairs where the function takes a value of v. Of course, if I pick, let's say, here's the set of pairs where it takes value v. If I take a different v, like a higher one, that's going to give us, it's going to have the same kind of curve shape, but it'll be pushed out a little bit. If I take a v that's smaller, it'll be pushed in, like so. So that would be the topographical map that corresponds to this three-dimensional shape that I tried to draw, not very successfully. Okay, so that's a little bit about multivariate functions. These are just a few examples. You can imagine, any kind of functional form for these things. Functions can be very complex or very simple, like these additive ones. Okay, that's it for this installment. The next installment we'll come back to multivariate functions, but then combine that with optimization, and I think we're getting close to the end of the series. All right, see you.